Welcome everybody to the webinar, Containerized CI/CD. My name is Andreas Fink. I'm a software engineer at CSCS. Together with me in this webinar is Theofilos Manitaras. He is also a software engineer at CSCS. I will first give an introduction of the CI that we have developed for future CI/CD on Alps, and Theofilos will give a more hands-on and go more into details what you should pay attention to when you do containerized CI/CD. So the first question is whether you want to, why do we want containerized CI/CD? One main reason is that we want to track the software dependencies for the reason that we have observed in the past that typically people depend on the state of a system, and that is something that we want to get rid of. So a pipeline should be self-contained and contain everything that needs to test the software fully from beginning to end. So it should just contain also all the dependencies. It allows you also to test updating your software dependencies without changing the software itself. So you can see performance or whether it still compiles while you only update the software dependencies, and you can roll back easily. It allows you to test existing builds on new clusters, while you might not expect the best performance on new clusters with an existing container. It might still give you a broad idea whether it works already or if you can expect issues there. It's almost decoupled from the host system. Almost, I mean that we inject the MPI library. We might inject some file system paths inside the container, but other than that, it's completely independent of the host system. You can basically test and build on your own machine, have a development cycle on your own machine, and once you're happy, you can say, okay, now I want to promote the whole thing to the HPC cluster and test it at scale on more than just a single node. Sarus container runtime engine allows us near native performance. That means that we get no performance penalty running inside the container or if you would run it on bare metal. So it's just the same. The idea of the CI setup is that we provide you with common CI job snippets that are maintained centrally. They are maintained in a repository which contains recipes that have the helper blocks for you to build your own pipelines, and you should reuse these blocks, because if we change something internally and we make sure that the helper blocks reflect the changes, so you will automatically have working pipelines if you depend on the helper snippets. If you just copy the snippets, that is what is technically happening if you just say extends in your pipeline. If you just copy the text, then you might suffer of upgrade paths that you have to update your pipeline to. We also provide base images that are maintained centrally. They contain spec and you can reuse them. I will talk about it a little bit later too. Yeah, so these are two things that we provide: base containers and job snippets, and you should depend on them. Internally, what is happening is that you can still continue hosting your software wherever you have it. It can be on GitHub, it can be on GitLab, it can be on Bitbucket, it can be on another GitLab instance, so it doesn't have to be gitlab.com. Technically, what you have to do is that you have to set up a webhook, because the whole CI is event-driven. So the Git provider will send webhook events. These can be push events, these can be pull request events or comment events. And there is a middleware sitting on CSCS side, which is listening to these events. And according to the event, there is some action being triggered. Technically, what we are doing is that we mirror your repository, or maybe not mirroring, but we copy the relevant code that is needed for doing the CI to a repository at gitlab.com. And then we leverage on GitLab CI itself. So the documentation of GitLab is a good starting point, or a good reference. It's not a good starting point. In case you're wondering what happens with private repositories, we make sure that if your repository is private, it will also stay private on the GitLab side. So there is no exposure additional to if you're using this CI setup. The triggers for pipelines are the typical triggers. So we can have automated triggering on push events. So you push to branch main, it will test the branch main. We can have PR event triggers. That means that if you open a PR that targets one of the CI-enabled branches, it will automatically trigger if it's inside in the repo. If it's coming from a fork, it will not be triggered automatically unless this fork is from a trusted user. The setup of which branches are CI enabled and which users are trusted can be done by you. There is a little setup site where you set up for the pipelines which users you trust and which branches you want to test the pipeline on. If, for instance, somebody opens a PR from a fork and it was a non-trusted user, then but you still want to run the pipeline, there is the option to drop a comment, CS CI run, and then you can have multiple pipelines. So you can have the pipeline name there, which one you actually want to run there. Again, this only would trigger the pipeline if the comment is from a trusted user. You can set up on the setup page a cron schedule that would run builds periodically, or you also have the option to send with your credentials. So you need to, this is an authenticated endpoint. You can send a trigger and you can tell to test main or whatever, any reference you can test there. So from the architecture is, I hope you see my mouse. So the public repositories, they are where your code sits, and that's the repository that you interact with. So you will continue working only with your public repository. These public repositories, as I said, they will send webhook events, and that's the crucial part because that's what we request you to do to set up a webhook. And this is the middleware that will receive the webhook. It will create a mirror in GitLab, and GitLab will then start the building pipelines. Basically, there is a GitLab runner to build a container image, which will then be pushed to an Artifactory. And then in a second step, there will be a run, which could be a GitLab runner. Unfortunately, there is written Eiger, but we don't have it on Eiger, but we have it on other Alps infrastructure, but we also have it on Pitstein. And yeah, so this is the architecture of the whole thing. Keep in mind that you typically only interact with your repository. So you don't interact with this mirror repository. This is just a technical detail that I mentioned. So you're aware that there is a second repository, and you will get a notification in the end to your repository if the build was successful or if it was not, and you will get a link, and the link will point to the log files inside this GitLab mirror repository. So that's when you would land on the GitLab repository. As I mentioned, if you have a private repository, then the GitLab is not publicly visible. So we have to redirect you to some website that sits on the middleware, and that will show you the log files from GitLab. So the middleware can access GitLab, but the outside world cannot. So then you would get a link that points to the middleware, and you would see the build results on a simpler website. Yes, so a typical CI setup looks like this. You start with a Docker file that describes your base dependencies. You run it through the container builder, and you build the container base image that will be persisted in the Artifactory. Based on this, you have a second Docker file that starts with this base container image that was just built. You build the software inside, and with software, I mean basically the source code that is part of the repository that you want to do CI on. Again, this will be put in the Artifactory, and then from the Artifactory, we go to the HPC cluster where we pull the containers and we test different test suites that you can run there. And of course, from any part, it can be failure from any path or success if all of this was successful. To mention is that this base container image is slow changing. That means that you see, I mean, you do changes to this Docker file very rarely, only when you want to update dependencies or you have a new dependency, then you update the Docker file, while this is basically rebuilt on every commit. So this is what you really want to test. Maybe to show the differences, traditional CI is that you go to the host system, you install all the dependencies once manually, and then you set up CI to depend on this dependencies that you have there. And you build it bare metal and you test it bare metal basically all on the same system. Containerized CI is that we build a base container image. We don't rebuild it every commit, and Theo will show how this can be done. We build then based on this software that is based on the first container, and then we test. While the build can be on a different node than the test is actually happening. So on a technical side, these nodes are in a Kubernetes cluster, and they are meant to build containers, and they're optimized for building containers, while testing the software is optimized for Slurm and HPC software. So this is like a little bit of separation of concerns. We have dedicated build nodes and we have dedicated test nodes. So some boilerplate that you will always have in the CI YAML, and we will share the slides with you later on, and there are links to different things. So for you as a user, this is the entry point to containerized CI. So this is where you should go first. There is a tutorial, there are links to all the other bits and pieces of CI. You will see this very often. So first of all, you include this recipes that I said. This is where we centrally have all the snippets that you can depend on. And then typically you will have stages. I make it super simple, 2 stages, build and test, just so the next snippets might make sense in the next slides. Then jobs typically look like this in the YAML file. You give the job some name, whatever you want, so you can choose any name. Then you say extends, and then you depend on one of the snippets that are defined in the CIX YAML. You will see on the other slides what extents make sense. Then you have to put a job into a stage. So this job I just put into the stage build, and you can pass variables to the job. That means that during the job execution, you will have the environment variable, my custom variable, and it will have the value some value. Second variable, another variable, value 42. Jobs that are in the same stage, they will run in parallel during CI run, and jobs that are in consecutive stages, they will wait. So first a full stage has to finish, and only then the jobs from the next stage will start to run. So this is an implicit barrier which you can make use of. So for building container images, there is the container builder runner. Basically, you have to specify extends container builder. You put it in the stage, as I said, and it has two variables. There is the Docker file, which says where is the Docker file inside your repository, and you have to give it a name. The name has to start with CSCS registry path, and from there on, you can basically define your own workspace, however you want to organize your container images. We don't restrict you which subdirectories you create or how you call your images, as long as it's a valid OCI container image name. Some container image names are invalid, but you will get a rejection message then if you choose an invalid name. So yeah, the Docker file, just keep in mind that this is a relative path to the root directory. So even if your YAML file is not sitting in the root directory, this still has to be relative to the root directory. Do not start with a slash. And as I mentioned, it's not relative to the CI YAML file. You have to push the container images inside your namespace of the Artifactory. So CSCS registry path contains the namespace of your project, and inside there you can push inside any subdirectory. There is a special case if you push inside the subdirectory that has the name public. So let's say instead of subdir, this would be public. Then this image can be pulled on on CSCS infrastructure, can be pulled without credentials. So that's one way how you can manually pull the container image afterwards and test. I left 2 links for the image retention policy. So we are deleting images regularly, and we are the runner itself supports a couple of more variables. You just go to the documentation if you need some advanced usage. Then for building base images, as I said, we have base containers that we provide, and these base containers they have spec installed, and it's not only spec, it's spec with batteries. So if you want to make use of them, and I encourage you to use it because they're much easier to use than setting your spec environment yourself. Basically, it contains one script that is called spec install helper, where you give as first argument the target system that you want to target. So there could be Dyn MC, Dyn GPU. I don't know if you know Hogand, but this is our Alps test cluster that we have internally inside CSCS. There would be Hogand Zen 2, Hogand NVGPU, and things like that. And then all the other arguments, right now, they are just valid SPAC specs. So you specify which packages you want to install, and it will just take care to get everything up and running. You will get the right micro architecture for the target system. You will get the correct spec variants. So there is also a CUDA version of this, and you will also get the correct MPI. So MPI hooks work out of the box. So this is a helper base container that makes it easier for you to build a base container with the base dependencies that you depend on. The whole thing is hosted also open source, and you can check the recipes how we built these containers, and there is also a little bit more documentation on that. Then running the containers, again, we have to choose the runner, and it always starts with container runner and then followed by the system. So in this case, I choose Dyn GPU. Here we have the image that we basically were building before. I don't know if you can remember it, but this guy, so we stored it in the Artifactory under this name, and that's exactly what we want to run now. So these two have to match. So we first built a container, and now we have to match that we want to run this container. We put it in the stage test, and here you can put whatever you want in the script. So this is basically the command that you need to do to test your software. You can work with all the Slurm variables. For instance, this would run on 2 jobs, and it would inject the MPI hook of Saros. So if you use MPI, then you depend on the hook of Saros to replace the MPI implementation inside the container with a host MPI. And yeah, by default, we do not fetch the source code on this runner because it's almost never needed that you fetch the source code again, because it has all the software already built inside the container. So typically it's not needed. But in case you need it, you have to set the variable git strategy to fetch. It's also mentioned in the documentation, and there are more variables that you can use. Again, please refer to the documentation of this. To summarize, what I want to get along to you today is that what we want with a new CI setup is that we want to separate the concerns. So CSCS is providing the building blocks that optimize for performance, and we know our systems very well, and we know exactly what needs to be done. And instead of telling you all the optimization tricks that need to be done, we rather want to keep them centrally, so we can maintain them centrally, and once we update them, all the users benefit automatically of it. So this is what will change. You always should include the helper YAML in your pipeline YAML file. I want to mention again the spec base container images that we offer, which has the spec install helper to build the base images. Theo will talk a little bit about the container builder dynamic name. Use it if you to build your base image, but only when it changes. So this block helps you getting this done. And there are a lot of example projects, or let's say not example projects, but projects that are already using the CI setup, and they are all linked from the CI documentation. If you scroll to the down, you will see you will see a couple of links to public repositories that are using the CI setup already. Some things that are missing, but will be done, is that we don't have building blocks for future Alps hardware like Gracehopper, but we will work on it as soon as we have the hardware available. At this moment, it's not possible to store variables or secrets that would be injected with every pipeline run. So it's not really possible to, let's say, report to CodeCoff or something like this, because then you would need to store a token. But this is being worked on and probably being done in this year. We need to integrate also CSCS single sign-on. And in the future, we would like to have a Firecrest integration that would allow us to even dispatch jobs to different compute centers. For instance, Lumi will have soon a Firecrest also installed, and then you could have one pipeline that would test simultaneously on Alps infrastructure and on Lumi. And if you have access to even more compute sites that install Firecrest, that would be even better. As I mentioned, this is about containerized CI, and we encourage you to use containerized CI, but with the Firecrest integration, we might be able to offer bare metal access. We are not entirely sure if we do this, but it would be possible then. And we need the Firecrest integration to have a better integration with Reframe, because right now it's a little bit, let's say, flaky setup if you want to combine both. Yes, so that was it from my side. So now Theo will take over.
Okay, so I can start sharing my screen.
Yeah.
Let me know. Is everything showing fine?
Yes, looks good.
Okay, can you hear me also well?
Yep, everything fine.
Okay, cool. So we can have all the questions in the end so that you have the full picture. So my name is Theofilos Manitaras, and I will pick up where Andreas stopped. So I will present also my part on this containerized CI/CD. I will more or less focus a little bit on how the pipelines look like and how a test run pipeline looks, and what are best practices that you have to follow in general when you are moving from a bare metal setup to a containerized workflow. So Andreas mentioned what are the advantages of using containers in general. So I will show you now the 5 main topics of this presentation that I have. The first one, I will again repeat how the creating of container images work, then how you test these container images that you created in the first place, because it's important that not only the building phase finishes successfully, but you have to test that actually the container that you have built is running. And at a later stage, you might need to test that it's performing well also. Then I will talk about multi-stage builds and image splitting. It's a pattern that comes along when you start working a lot with CI and containers together. Then I will focus on a very important point, that you have to build the container images for the target architecture, and you'll see more details there. And then I will just mention the image labels as something extra that you can add in your container images, so that you have more information that you can extract when you inspect images. So let's start again with something that Andreas mentioned already about creating container images. So creating container images is pretty straightforward. I have a link here that I will go after. But basically, you have your YAML file in the GitLab CI or on GitHub, where you host your code. And the only thing that you need to include, this is the boilerplate. So this is the templates that you have to include, that we have created at CSCS to make your life easier. Here I have a typical GitLab pipeline syntax that I have only a single stage at this point, a build stage. And then in order to build your software inside the container, you have to extend this container builder here. So here in red. And then the only mandatory variables that are needed are the persist image name, where you specify where this container image that is created is going to be stored. It has to be relative to this CSCS registry path. And then actually what Docker file relative to the source code directory, the source code root, you have to use, so that the pipeline creates the image for you. So let's go directly in the pipeline in a GitHub project, a GitHub pull request that shows this. So here you will see that in the files that are added, you just have your pipeline that contains more or less the information that I just showed you. Here is some a CMake file that is needed for your source to build. And here you have your Docker file. And this corresponds to the Docker file that I'm pointing in the Docker file in the build pipeline here. So this Docker file will be used to build the image that you want. And the resulting image will be saved in this artifact repository path here. For more information, you can follow another link, basically, and here you can find more information on what is available for you as extra variables, apart from the mandatory ones, to make your life easier. Now that we are at the point that we have built the container image, so let me go back again and show you also how the pipeline looks like on the CI side. So here I can visit the pipeline directly, and I can see the pipeline is build software, go and check my output and everything. You see that the image built correctly, was pushed to the repository that you specified. So yeah, I will look at, there are some questions, but I will look at them when I finish the slides. So let me go back to the presentation. So now that we have successfully built a container image, we have to test it. Here I will just run it to see that it's running fine, but you have to make sure that not only you build the container image successfully, but it actually gives you the results that you want when you run it. So here again, we have some boilerplate code that I don't include here, since you include again the templates. The different thing now is that you want, in a different stage, to test the actual software. And here you have to extend based on the actual compute node that you want to run, you extend a template that is the container runner in DynamC. In practical terms, this means that this container run is going to take place on the multi-core partition of Dynt. So here you specify again the image that you want, which corresponds to the image that we have built on the first stage. Here it's very important to give what the container is going to execute, the command that the container will execute. This will be executed in the container itself. And here are some variables that affect the slarm allocation and also how Sarus executes the containers. Here you see that I want this execution to be for this execution to use 4 slarm tasks, 4 MPI tasks more or less, a single node. Here is another slarm parameter for the label IO. And here I tell Sarus to use the MPI hook to replace the MPI inside the container with the host one, so that you get the best performance on the host that you are going to run. This is something specific to Sarus, so that you get actually the best performance according to the interconnect that Dynt has. But it's similar also on other systems. So let's go and see how this looks like. So here we have, again, a pipeline that has 2 stages. The first stage is similar to what we had in the previous pipeline where we were building the container, but now we have this additional step here, the same Docker file as before, but now we are actually going to run also the container. So here I'm going to the pipeline, and you see now that not only do we have the build, but we have also the testing job for that, and we can see that we got hello world from the 4 tasks that we have asked. Here you will see some more debugging information of how Sarus executed this job. So let me go back. So at this point, we know how to build container images and how to run them using the CI pipeline. Now I want to focus on a different topic, which is a more advanced one, and it's multi-stage builds in the first place, and reusing or splitting images so that you get a better use of your time and make it much faster to test your software. Multi-stage builds. They are an essential mechanism during the image building. With them, if you're not familiar with the concept, but you're familiar with Docker files in general, you are able to use many from statements inside the Docker file, like you see here. I have the first from and another from here. So basically, this Docker file will start building the first image, and I have used a name here for helping me recognizing which image is what. So here I say that the first image, which comes with the first from, I name it the builder. Now I have all the Dockerfile steps that were going to be executed from the builder. And then I have a second stage, that's why they are called multi-stage builds. And in that second stage, I start from a different image, which is a lightweight one, but I copy something that I need from my first image. So again, I start with a container image that contains everything that is needed to build my binary. So I have here all the steps to build my binary. And then, since I don't need the compilers anymore because my binary is built, and I start from a more lightweight image that doesn't contain the compilers, only the libraries that are needed for my software to run, and I copy the binary that I built from the builder image. So this is the syntax here. I copy from the builder, and I have the source for the binary that comes from the first image to the target path in the second image, in the runtime one. This is a single Docker file. So when I say to the container platform to build this for me, if I don't specify otherwise, I'm going to get back as a result the runtime image that has also the binary that I built using the first one. So again, here I mentioned that artifacts can be copied from one stage to another. And this multi-stage build mechanisms allows us to create lightweight images. So the final image does not contain the compilers and all the necessary stuff that are needed, like the header files and everything that I would need to build my binary. Now, I will show also how it looks like in terms of pipeline after. So image splitting now. Andreas, do you think I can stop for some questions now, or I should continue?
We can maybe answer a few questions now.
Okay.
Yeah. Maybe I can take the first.
Okay. Yes.
So I'm taking this one that Matze asked, and he said, if we have scientific data stored at CSCS that is too big to be put into a container, can one access that for testing purposes via the CI? That's a very good question. So I'm not entirely sure how your data currently is stored, but I guess it's somewhere on the target system already. Let's say Pitstein. So what we can offer is that the data would be publicly accessible, I guess, because that's one of the limitations that we currently have. And then basically on the CI side, there would be a named storage. Like there is data for icon that is already registered, and that can be requested to be also mounted inside the container. So once it is registered as a name under some name, right? You can basically tell through a variable, I want as an additional storage, or not additional data, you want this to be also mounted inside your container, and then the data would be available inside your container too. So it must be stored on the system itself, and it must be accessible by some username that is running the CI pipelines. So that's the two limitations that are there. I hope that answers the question.
So I can take the second one, like, are the programming environment images going to be provided alongside the Ubuntu ones, like programming environment Cray, NVIDIA, GNU? So this is another good question. For the moment, I'm not sure I have the answer about that, because this depends on what HPE would provide, if we could provide such images to be used, which would offer this programming environment, like having an image which offers the programming environment Cray, the NVIDIA, and GNU. So that's something that I don't really have a question at the moment, an answer at the moment, but it's a question to be asked by ourselves to HPE, because those contain proprietary stuff, so they are not accessible like via Docker Hub or via Quay or all these public repositories.
So yeah, I can take the next one. So Pramod asked if if this is connected to Slurm compute nodes, how the security aspects are handled. If we have PRs on open source repos that will trigger such CIs, what are existing policies, general recommendations? So I mentioned that when a pipeline is being triggered, and I mentioned that it is being triggered if a PR is opened or actually a PR is changed. This applies only if the PR is coming from inside the repository. So our trust model on the whole concept is that people who have access to the repository, they basically can run jobs on the CI. That's basically the trust model that we have. So the less people have direct access to the repository, the less people can run automatically. Then as a second option is that the PR comes from a fork. And then there is like a trusted user list that you set up, right? So you're the owner of the CI pipeline and you set up a list of trusted users. If the PR comes from a fork of a trusted user, it will be tested automatically. If it doesn't come from a list of trusted users, then it will not be tested automatically, but it can be triggered by one of the trusted users.
Okay, let me go on with the slides, and then we can answer the following questions if we have time in the end.
Yeah.
Okay, so I mentioned multi-stage builds before, but another typical pattern that emerges apart from having can you mute yourself, Andreas? So another pattern that emerges when you start using container images in your CI/CD pipelines is that many of the image components, like library dependencies and like compilers and all this stuff, change at a much lower pace than the actual software being developed. So you push a small change to your source code, and you don't want to build the whole Docker. You don't want to build the whole image from scratch again, like build the dependent libraries and then implement the build your own software and test whether your change works or not. And this is also very important and very serious, because building a container image and all of its components sometimes might take a long time, and you waste computing resources when you do that. And also you cannot, if the image takes 1 hour to build, you cannot push every 5 minutes and wait for the whole image to be built. So the solution to the above is to split the image in 2 parts. So instead of having a very big container image that contains everything, you build an image that contains the built environment, that this image can be updated when you want to update the dependency or start using a newer container-based image. And then you have an image that only builds the software that you actually want to test, and using the first base image as its starting point. Let me show you what I mean. So here we have the 2 stages. We have the build base, which is going to build your base image when you need, and it will retrigger a build only when the base image changes. So you update your dependency and you want to propagate this update to your software. So here you extend the container builder dynamic name, and this is very useful because it's used to propagate the base image. And then you have this special variable with watch file changes, and you specify that you want to build only when there is a change in this base image Docker file. So as long as you don't update it, your base image will be reused if it's there. And here you have the persist image name. Then on the second stage, where you actually build your software, you extend the typical container builder as before, but now you pass the base image that is injected from the container builder dynamic, and you can pass it as a Docker build argument, which will inform the Docker file that will build your source code, that the base image is the one that is referred to in the build base phase. Let's see how this looks in practice. So here I have the PR about splitting a container. Again, we are going to build our hello world example. And here is the whole pipeline with the build base, the build your actual container image with the software that you want to test, and then the run phase where you test your software. And here you see the difference between the base Docker file, which has many steps, and the actual Docker file that's going to be built more often. So here you just accept a build argument, which is the base image here, which is what is propagated from the pipeline. You see it here. I pass it as a Docker argument, the base image. And this just copies the source code, which is the update version that triggered the pull request, triggered the build in the first place, and just makes your source code. And then you can use this image to test your software. And the pipeline looks like this. Build base. So this is going to be triggered to do some actual thing only when there is a change in the base image Docker file. Otherwise, it will reuse the already available base image. Then you build your software here. It's much faster than building your image from scratch. And then you test your software as normal. You'll see here, hello from the 4 ranks. So again, you split the image in 2 parts. The one that contains all the dependencies, the compilers and everything, the things that do not change very quickly. And the other one just copies your source code and builds based on the first base image. Now, a very important point that I want to stress is building for the target architecture. Typically, when you're used to building on the actual bare metal machine, you might rely a lot on auto detection of the system, and based on the architecture that is automatically detected, the compiler chooses everything for you. But in the container image pipeline, this is different. And this is different because the container image might be built on a machine that is not the target machine that you're actually going to run your software. So you can build an image on a Kubernetes pod, for example, on some inside a Kubernetes pod, and this might reside on a completely different system from your target one. It might not have GPUs, it might not have the high-speed interconnect, it might not have the same processor, so it might have less performant processor without specific vector instruction, and so on. So relying on the auto detection is a no-go here. So you should specify explicitly what is the target architecture that you want to write the image that you're building, and make sure that all the settings are in place. CSCS offers a list of essential building blocks similar to the container building image, to the container build template, so that this compatibility and performance of the resulting images according to the systems that we have in place and we are going to use to run, so that you can use these essential building blocks. And these come in 3 flavors. We have various base images. Here I have a link. You have the CI pipeline templates that you saw also, and there are also several more to help you, and more are coming to support also the different architectures. And you have helper scripts like the Spack install helper that Andrea showed before that can help you so that you don't have to specify every architecture characteristic by yourself. But I have here an example how it looks like when you do not rely on any of these helper features. So here I have a container image that I want to build. Here you see that I have a build argument with a target Haswell architecture, but this I can change via the build arguments that I pass to the image. And this target build argument is propagated to the target that Spack is going to use for the packages. So I can build on a Haswell machine, but I can target another architecture. I accept it as an argument and I pass it to Spack. And therefore, for using the same image, I can pass target Haswell here. I can build for one specific image with a specific tag for Haswell and one for Zen2, and I don't care where this image build procedure is going to take place. And I can show you how this pipeline looks like. I have here how it looks on GitLab, but we can look at it on more detail. So here I have the Docker file, and here is my target that I can use as a build argument. I can pass via build argument. I use this with Spack, and I can use it even to build different MPIs based, for example, on the target. Here I use mpich for my Haswell system, and I use mvapich for if the system is different than Haswell. And then I can run on Haswell. Here I use container runner giant GPU and the Haswell image. And here I run on Hogan, which is our test Alps system. And here I use the Zen flavor, the Zen2 flavor of the image. And if we go to the pipeline, build Haswell, build Zen, run Haswell, do everything, run Zen. So with the same pipeline, I built different images with different characteristics and different target architectures. I don't care where these images are built. What I care about is that they are built with the target system in mind. So all the optimizations are taken into account. And this is also related to systems that have GPUs, for example. So you might want to target a particular GPU architecture. So you have to pass the compute capability for that particular architecture, no matter where you build. And for another system, you might have a different architecture or a different, you might have on one system an NVIDIA GPU, on another one on an AMD GPU. So you can have a unified image and based on the target architecture, change a little bit how this takes place. And to finish, I will talk a little bit about image labels. So this is just a mechanism to add useful metadata to the container image. So using the Docker label statement here, you can pass various labels which are added as metadata to the image itself. So when the thing that you have to be careful is that the labels go together with a particular from here. So these labels you see here in the second step are going to apply to the Docker image that I want to build here. Also, if you start from a base image, unless you override the labels, they are propagated from the base image. So you will have extra labels if you add here. And then you can access the labels with image inspection with tools like Docker or Scopeo. With Docker, you can inspect using the image name, and I pass here some format option to get a different, better looking result. So here you see directly that I have access to these labels. With Scopeo, you can even inspect an image without first downloading it. So here I inspected the Docker image and directly I have my labels here. So this is very useful because you might have many different images and you want to inspect what the metadata of these images without even needing the need to download in the first place. So that was it from me. Thank you for your attention. And we can go on with the questions, I think now.
So right now there are no open questions. Maybe just to mention once again, so we have been using this webinar repository, and that is hosted on github.com/thinkandreas/containerized
Yeah, let me show it
CI
also.
dash.
So
So containerized CI webinar. So this is where we will also upload the slides later on. So you will find the slides in this repository after the talk. The five different examples that we were showing, they're all pull requests. The first three they are based on top of each other, while 4 and 5 are the two that Theo just presented.
I have here one with labels as well.
Yeah.
So
you can use this to look also at examples, and the slides will have all the links available. Then Lucas has a question. How do I connect a mixed workflow from GitHub with the CSCS workflow? I want to publish my package only if the tests on CSCS succeed. Can do that on CSCS because secrets are not supported yet. Yes. Good question.
For the GitHub part, these are more or less, this is a GitHub repo that more or less, when you open a pull request or you make a change to a pull request, this triggers a pipeline which runs on GitLab. So the pipeline, you can host your code on GitHub and the pipeline runs on the GitLab setup. And now for the second one, yes, it's something that...
So Lucas, I allowed you to talk. So if you unmute yourself, you can. So basically the question is what would you like to upload afterwards? Because that can be a job inside the GitLab itself. But okay, so so the missing feature of secrets is the problem, right? If I understood correctly. Otherwise, you could upload directly afterwards from the CSCS pipeline. Okay. Yeah. Yeah, I mean, right now there is no easy. You have to wait for the feature, I guess. Then until then, I don't know. I mean, there is no easy way at this point, I guess, unfortunately. No more questions. Yes, then I would say thank you very much for joining the webinar.
Yes, we're going to upload the slides so that the slides have the links also so that you can easily navigate.
Yeah, exactly. Then thanks very much.
Thank you very much for joining.
Have a nice afternoon. Ciao.